Alright, so I think I'm recording. We're taking a look at these rational functions, and they're asking us to find three things: the domain, and to examine the domain and determine if the graph of the function has any vertical asymptotes or any holes in the graph. And if there are holes, to give the location of where they occur, and if there are vertical asymptotes, to write the equation of that vertical asymptote. So whenever we're finding the domain of a function, we are concerned with two things: division by zero and avoiding the square root of negative number, well, even root of negative numbers. But since we have a ratio of polynomial functions, we don't have to worry about even radicals, even roots, because there aren't any. So all we have to worry about is division by zero, which is going to use either our skills of factoring, or quadratic formula, or completing the square, or higher order polynomial functions using the rational zero theorem. So let's use what they taught some of the students. If you took Algebra 1 over here at Northview, when you have a leading coefficient that is different than 1, and especially if that leading coefficient is a composite number, if it's not prime, then to factor it can sometimes be difficult. So an organized way to apply the distributive property to factor this trinomial is to use what they refer to, what they call as an X method. They draw an X over the middle term. So the top of the X, they take the first term times the last term. So we've got 36x squared, and you now look for two values when multiplied together give you the 36, but when added give you the negative 13. So a negative 9x and negative 4x appear to do the trick. Now, when the leading coefficient is just 1, you simply use those as your factors. But with the leading coefficient not being 1, they suggest that you factor this in the form of a table. Along one diagonal, you write the first term and the last term of the trinomial, provided it's in standard form. You know, we're always working, and also provided that there's no greatest common factor among any of the terms. I don't know if this X method, I doubt if it would always work if you had some common factor in your original trinomial. The values that you found in your X, they go along one diagonal, and it's interchangeable. It doesn't matter whether I put the negative 9x here or the negative 9x there. When I do have a positive in this lower right corner and the diagonals are negative, I do need to have negative 9 times negative 1. You can see that here the common factor is 9, but I need it to be negative because here there's not a common factor, and I need it to this product to be a positive 9. So a negative 9 times the negative 1 is positive 9. And if I look here now, I have 4x, and 4x times negative 1 is negative 4x. And then vertically, when I look here, these are prime with respect to each other, the numbers, so they just share an x in common. And 4x times x is 4x squared, and negative 9 times x is negative 9x. So everything works out fine. And this numerator, or what was on the numerator? No, the denominator, I got to keep track of what I'm doing here, is x minus 1 and 4x minus 9. Now the numerator is so similar. Let's go ahead and do that now as well. My middle term has changed. Instead of negative 13x, it's negative 12x. But the idea remains the same, that if we need two numbers that when multiplied together give us this 30x squared, but when added give us this negative 12x. So 9 and 4 is what we used last time. 6 and 6, negative 6x, and a negative 6x works because negative times negative is positive, and when we add these we do get the negative 12x. So when we come down in our table this time, we have the same diagonal across here, the first term and the last term of the original expression, my 4x squared and my 9, and then I take the values that I found from my x and put them along the other diagonal. So I've got negative 6x and negative 6x. So since this diagonal is both negatives and this is positive, I need negatives on the outside here. A negative 3 times a negative 3 is positive 9. If I look horizontally here, these are both even numbers. They both have an x, and 2x times negative 3 is negative 6x. Vertically, these are both even numbers, and 2x times 2x is 4x squared, and 2x times negative 3 is negative 6x. So we have now found the factors here. 2x minus 3, and since there's another 2x minus 3, it was just 2x minus 3 squared. Alright. You know what? It did work. I'm going to start this video over because I had a greatest common factor. No, I didn't. Okay, there's not a great... At first I thought... I was thinking it was greatest common factor of 3, but it's not. It's, hey, save the video. I don't know. I stayed up too late last night. Alright. Well, I'm ready to find the domain now, so let's get rid of this work. Alright, so the domain, we want to avoid 1. We want to avoid 9 over 4. That's an improper fraction. That's bigger than 1. So my domain excludes 1, and 1 is less than 9 over 4, and it excludes 9 over 4. There were no common factors, nothing canceled, so there's no holes in the graph. There are 2 vertical asymptotes because since this is reduced, that my denominator here, these values that I exclude from the domain are either going to appear as holes or vertical asymptotes. Since there's no holes, both of these have to be vertical asymptotes. You want to give the equation for vertical asymptotes. So let's emphasize that it's a line, not the x-coordinate of a point. X equals 1 is one vertical asymptote, and the line x equals 9 over 4, which 4 goes into 9 twice, and it has a finite decimal representation of what, 2.25, 2 1/4. Alright, so let's go confirm this on the online graphing calculator, this Desmos.com. Alright, so let's put parentheses around this numerator to make sure that it divides all the terms, not just the last term, by my denominator. I've got 4x squared minus 13x plus 9. Now remember, terms don't cancel. You have to resist the temptation. This 4x squared and this 9, they do not cancel. Those are terms. Terms, only common factors cancel. And so we believe that there was 2 vertical asymptotes, and there they are. One at x equals 1. Let's x equals 1 and the other at x equals 9 over 4. Let's change those to both be blue and both be dashed. And we verified that. If you zoom in, you can see that it never touches this vertical asymptote. The graph doesn't. Alright. I hope that helps, and I will talk to you later.